Okay. Hi, everyone. Good morning / noon / afternoon, depending on your time zone. Welcome to the next Extremeline Probabilistic webinar, which will today we will have Asaf Ferber speaking from University California, Irvine, and he will talk about induced subgraph with prescribed degrees modulo Q. And before we start, just a few remarks regarding the organization of this webinar. So this webinar is going to be recorded, and in particular, I should say that if you don't want to be recorded, then don't ask questions and don't switch on audio and video. Also, if you have questions for Asaf during his talk, please write it in the chat. And quite often it actually happens that the question is answered by some other participant before we even notice. But if not, we will tell Asaf that there is a question and ask him to answer it. And less important, or questions that can be answered after the talk, maybe keep them after the talk, where we open a question and answer session when also everybody can get unmuted and ask the question in a more human being form. And also we intend to split the question and answers into two parts. The first one will be still recorded, but then we will have more sort of informal, non-recorded part of it afterwards. So, okay, I hope I haven't forgotten anything. Oh yeah, last thing, the slides are on already, the slides for Asaf's talks are online, and I'm also sending a link to it. Alternatively, the link is on the webpage of the webinar, and I hope I said everything. So Asaf, the virtual board is yours.
Okay, thank you. So first of all, I want to thank the organizer for inviting me for this webinar. So forgive me first of all, and also forgive me if I'm not that sharp or nice. For me, it's 6 a.m. So I think that even at 9 a.m. I'm not that nice. And today I want to talk about induced subgraphs with prescribed degrees mod Q. This is a joint work with Liam Hardiman from UC Irvine and from Michael Krivelevich from Tel Aviv University. Okay, so let's start. So please don't hesitate to ask me questions in any moment. I will try to check the chat from time to time. So let's start with the following riddle. It is one of my favorite riddles in graph theory. So I just copy pasted it from the book of Lovas, the combinatorial problems and exercises. It's problem 517C. Assume that at each vertex of a graph, there is a light and a button. At the beginning, all lights are on. Pushing a button will change the status of the light at the vertex and its neighbors. Show that one can push some buttons so that all lights will be turned off. So I'm curious, like, how many people know this riddle? So let's try to understand what's going on, some simple cases. So for example, imagine that you have a graph with all the degrees even. Okay, so in this scenario, it's very easy to switch all the lights on if we start with all the lights switched off, so we can turn them on by just pressing all the vertices, right? Because if you think about it, just fix a vertex. So you pressed all the vertices in the neighborhood. So basically you didn't change it because the degree is even, but you also press the vertex itself. So you switch every vertex. Now, if you don't know this riddle, so there are many proofs for this specific riddle. So one of my favorite is like the linear algebra approach, but you can also do just some direct induction, and there's a more clever construction. In the book of Lovas, there is a better, like a really sophisticated induction, also quite short, but I will talk about it soon. So a hint for a linear algebra approach is just, let's try to think about it for a second. You want to show that every n by n symmetric 0, 1 matrix A with an all one along the diagonal. So you want to show that for every such matrix, there exists a solution to the system of linear equations AX equals the all one vector, where X is a binary vector. Is it clear? Yeah, that's the problem with Zoom. I cannot see anything. Okay, so hopefully it's okay. And stuck. Good. So a nice observation is that the above riddle is equivalent in terms of graph theory. It's equivalent to the following problem. You want to show that for every graph, we can find the vertex partitioning into two sets, such that the induced graph on the set V1 is an even graph, meaning that all the degrees are even. And for all vertex from the outside, from the other part, the number of neighbors of this vertex into the even graph is odd, right? Like imagine that we have such a partitioning, then we already have a strategy, just press all the vertices in V1. And then, so I don't know if it's a good enough motivation or not, but it is natural to ask for partition satisfying some other constraints, mode 2. So for example, in one of the solutions for the above riddle, actually the solution that appear in the book of Lovas, as an intermediate result, Galai in 1971, which is unpublished, he proved that every graph can be partitioned into two even graphs, meaning like two graphs that span only even degree vertices. And he also proved, actually it's an easy corollary from the first bullet, that every graph can be partitioned into two sets, one of which is even and the other one is odd, meaning that odd, naturally, it means that all the vertices are of odd degree. And let's see, so it's not even a hint, right? Because if we have the first bullet is a bit complicated, but if you believe these two theorems, so let's show how Galai's result immediately imply a solution to the riddle. You can just take a graph G, add a new vertex and connect it to all the even degree vertices. And now you can partition the new graph, right, with the new vertex V into two even subgraphs. And without loss of generality, we can assume that this vertex is in V2. And therefore, V1 union V2 minus V is the required partition, right? Because indeed, take any vertex. So you know that V1 spans even degree and V is in V2. So you also know that in V2 union V, all the degrees are even. Okay, and because we connected V to all the even degree vertices, so you know that every even degree vertex must send like odd number of neighbors to V1, and clearly every odd degree vertex should send like an odd number of vertices into V1. Any questions? No. Okay. And another immediate corollary from Galai's result is that every graph G has an induced even subgraph on at least half of the vertices, right? Because like the first bullet was that every graph can be partitioned, the vertices can be partitioned into two sets that both induces like even subgraphs. So at least one of them is of size at least half of the graph. And then you can naturally ask for similar results if we require the subgraph, let's say, to be odd. So let's observe that a subgraph, like an odd subgraph, cannot contain isolated vertices, right? Because isolated vertices are of degree 0. So we can restrict our attention only to graphs with no such vertices, right? So we can start with graphs with mean degree 1, and then ask what is the largest subgraph, like what is the largest induced odd subgraph of G. So some notations, so f of G denote the largest size of an induced odd subgraph. And in 1994, Caro conjectured the following, conjectured that there exists some constant such that every graph G with no isolated vertices, as that Fg is at least this constant times the number of edges. And there's also a construction, it's very easy to show that if you take, I think, a K6 minus a perfect matching, then Fg is at most Vg over 3. And the best known bound is due to Scott from 2001, and he showed that Fg is a big omega of, it's like at least like the number of vertices divided by log of the number of vertices. And in his paper, actually, he proved several interesting results and left some nice open problems. And today I will not focus, so we also have like a part on deterministic results, but today I will mainly focus on the probability related problems. So what are the problems that I want to consider? The following. So suppose that you give me some K between 2 and whatever, And let's consider Gn 1/2 just for convenience. Our results will work the same for GNP if P is not 1/2. So let's take a typical outcome of the random graph and let's fix some residue mod K. And you can ask what is the largest subset of vertices for which GU spans a subgraph with all its degrees congruent to J mod K. And another problem that he suggested is what is the smallest number T for which there exists a partitioning, sorry, for which there exists a partitioning of the vertex set into T sets, where all the GVIs, like all the induced subgraphs, they span subgraphs with all degrees congruent to say 1 mod K, but you can fix any residue that you want, right? Let's say all the degrees congruent to J mod K. Okay, so these are two problems that he considered or asked. And what is known, so he also showed in his paper, in particular, he showed that a typical Gn 1/2 satisfies that Fg is proportional to Cn, where C is of the form 0.7729. Basically, show the concentration result. This is the best C. And I just remind you that f of g is the largest induced odd subgraph, okay? So here I showed some concentration inequality that f of g is concentrated around its whatever. And another theorem, we showed that in Gn 1/2, typically we have a vertex partition into 3 sets where each set induces an odd graph. And this is almost best possible because clearly Gn 1/2 with high probability is not an odd graph. So you can ask whether you can partition to 2 or 3 sets. So for 3 sets, he showed that the probability that there is no such partition into 2 sets is at most 1/2 plus little of 1. So I think it's also interesting to try to prove it for 2 sets. We didn't try this direction, and I will give you some hints on very soon, like why it's a little bit harder. So let's try to get some feeling for the problem. So for example, let's try to prove that a typical Gn 1/2 has an induced odd subgraph of size at least n over 4. Do you have any idea? Right, so for example, what do we know? So we know that in typical Gn 1/2, we must have like with high probability, we have a vertex with degree at least n over 2, right? So we can take a vertex of degree n over 2 and consider its neighborhood as an induced subgraph. And on its neighborhood, we can apply Galai's theorem and partition the neighborhood into 2 sets such that, so basically we are done, right? Like, so we can partition to 2 sets which are even. And here we are more or less done because we want to add the new vertex. The only problem that we need to make sure is that at least one of the parts is of size odd. So what do we need to do? So we take like a vertex of degree n over 2 and we consider an odd sub-neighborhood of size roughly n over 2. And then we cannot partition to 2 even sets because we don't know what's going on. So we can apply the second bullet in Galai's theorem and partition the neighborhood into 2 sets such that one of them is an odd subgraph and the other one is an even subgraph. So we know that the odd subgraph is of size even. And if it's of size at least half of the neighborhood, we are done. And if not, so we know that the even subgraph must be of size odd because like we restricted ourselves only to odd number of vertices, right? And then by adding the new vertex, so we know that we have an induced odd subgraph. So this is like a simple exercise, and let's do something slightly harder just to get some feeling from the problem. But again, I'm not going to prove like Scott's bound. So let's try to improve it to n over 2. So this was basically the first observation that we had about this problem. So for the second bullet, it's like a simple exercise, but maybe I will, but I decided to write some words here. So by Galai's, we know that G can be partitioned into 2 sets. One of them is even and the other one is odd, okay? Now let's fix any partition of the vertices into 2 sets where the size of A is even. And let's choose a vertex in the part A and a vertex in the part B, just some arbitrary vertices. and condition on any outcome that you want on the complement, right? On A minus A and on B minus B, just expose all the edges in G and 1/2, except the edges that touching the vertex A and the vertex B. And now if we think about it for 2 seconds, you will see that the probability that the induced subgraph on A is odd and the induced subgraph on B is even is at most, let's say 2 to the minus n. Forget about the 2 for a second, right? Because you already exposed all the edges by the edges, but the edges touching only one vertex. So if you fix this vertex, so clearly it at most uniquely determine the relationship with the other vertices, right? You want it to be connected to every, let's say that I want GA to be, like I'm looking at A, so you want GA to be odd. So the vertex A should be connected to all the vertices which are currently of even degree and should not be a neighbor with vertices which currently have odd degree, okay? So you already know the neighborhoods list, so the probability is 2 to the minus n because A union B is everything, is a partitioning of V. So we know that the probability that A union B will be a decent partition, right? That one of them spans an odd graph and the other one spans an even graph. You know that this probability is roughly 2 to the minus n. And therefore, by a simple union bound, we can exclude all the partitions where A is not, where the partition is not balanced. So we can exclude all the imbalanced partitions. And we know that because it's a deterministic statement, we know that there exists such a partitioning. So we also know that with high probability, there exists such a partitioning where both sets A and B are of size roughly n/2. So in particular, it means that there exists a subgraph, an induced subgraph of odd degrees of size roughly n/2. Any questions? Okay. So now let's try to state our results for random graphs. So I need to introduce some notation. Hopefully it will not be too confusing. So suppose that G is some graph and you give me some, you fix some K and you fix some residue M. And now let's define FGMK, right? So remember that we had f of G was the largest induced odd subgraph. So now I just want to generalize it a little bit. So we'll define FGMK. It's the size of the largest induced subgraph of G for which all its degrees are M modulo K. Okay, so in particular, did I write it? No. So in particular, FG, we can write it as FG12. Okay, like that, it's the size of the largest induced subgraph of G for which all its degrees are 1 mod 2, or in other words, just odd. And also this definition is not some of the most general one, so we can even extend it further. So we can write, just give me any proportions, right? So give me any distribution of the residues, like alpha 0 up to alpha k minus 1, be such that there's sum to 1, and consider this distribution vector alpha, and we can define fg alpha k to be the largest n for which G contains an induced subgraph on capital N vertices, where for each I, the number of vertices of degree I mod k is exactly alpha I times n. Okay, if it's not an integer, you can decide in advance if you want it to be rounded up or down or up, just you want all the numbers to sum up to this capital N. So this is the more general one. So for example, if we take alpha m equals 1 and alpha I equals 0 for all residues which are not m, then fg alpha k is basically just fg mk. Any questions? No. Okay. So among other things, we prove the following theorem. We prove that for every Q, okay, so for some reasons, we are now like polishing the results, but so far, like we wrote it for convenience only for prime numbers. Hopefully it will also work for numbers which are non-primes. So for all Q prime and all distributions alpha, we typically have that Fg, like that f of G and P of G and 1/2 alpha Q is around Cn, where C is the largest for which some ugly inequality holds. Basically, we just want, like, whenever the expectation tends to infinity, so we want to claim that there exists such a set. Okay, so it's different for every distribution vector. We get a different C. So basically, we completely solve this specific one, and also the second theorem. regarding the partitioning, it says that for all q and all vectors v1 up to vq plus 1 in zq to the n over q plus 1. So let's assume for simplicity that n is divisible by q plus 1, right? Otherwise, like you just take some vectors in a smaller dimension space. So imagine that you fix some prime q and you give me q plus 1 vectors in zq to the n over q plus 1. These vectors are going to be the degree sequence. Okay, you can fix the degree sequence. So a typical GN1/2 can be partitioned into q plus 1 sets such that each of them has the degrees vector vi. Okay, so basically like it's not just about like one modulus, just give me any degree sequence that you want modulo q. So we can partition GN1/2 into q plus 1 sets that each of them has degree vector vi. So this is an extension of Scott's result. He showed it with q equals 2. Okay, so we do it for all primes and actually all degree sequences. And that's it. So in the language of matrices, the above theorem, the second theorem, which is a little bit more interesting than the first. So in the language of matrices, the above theorem just states that if we take a typical random and symmetric 0-1 matrix, so it contains a block diagonal submatrix with blocks B1 up to BT, all the same size, such that the sum of the columns or the rows, because it's symmetric, it doesn't matter, sums to some specific vector that you decide in advance. Any questions? Okay. So I want to talk a little bit about the proof, but now I just drew some picture for you, just to understand which ingredients do we need. So imagine that we want to prove the first theorem, right? The first theorem is just the existence of one part, which is large. So basically what we want to try to do is to do some second moment argument. So for a second moment argument, we want to calculate the variance. We need to think about the covariances. So imagine that we have two parts, right? We take two subsets and they can overlap a little bit. I think about it in terms of a matrix, okay? So think about it as two submatrices of the big matrix. And now we want to ask what's the probability that both of them are good? Let's say that both of them have like columns that sum to some specific vector. So you see in the intersection, so the intersection is a symmetric matrix, right? And here you also see a symmetric matrix. And this is a non-symmetric matrix, and this is also a non-symmetric matrix, but it's the same matrix, right? Let's call it, if this is like some matrix A, so this is A transpose. And we need to make sure, so for example, if we first take care of the, let's imagine that we have some lemma that tells us what's the probability that this big square is good, right? So we expose all the entries here, and now we want to be able to complete. So we need two parts. We need first of all to complete, to extend it to the symmetric part, and then to hope that the non-symmetric part will actually complete the vector, the degree vectors. So we need the following two lemmas. So just for simplicity, so I can also show you some proofs, and actually it's without loss of generality. We can think of our matrices as plus minus 1 instead of 0, 1, right? Because if it's not plus minus 1, if it's a 0, 1 matrix, you take a random graph, you can just shift it by the, okay, not really shift it by the all one vector, and then you get a vector which is like a, so if it's a 0, 1, so you want to shift it by subtracting the all 1/2 matrix. And we have the following two lemmas. So lemma 1, we showed that for every prime, at least 3, if you take M to be a random M by M symmetric plus minus 1 matrix, and V is any vector in ZQ to the M, then the probability that the sum of the columns of M, which is also the same like the sum of the rows of M, equals this specific vector, again, give me any vector that you want from ZQ to the M, is roughly 1 over Q to the M, meaning that we have an approximate uniform distribution for the degree sequence mod Q. And the second lemma states that if Q is at least 3, right, so this is for the non-symmetric case. For the non-symmetric case, we can think about it as a bipartite graph, right, with one part of size D and the other part is of size k minus d, and you want to be able to tell me something about the degrees from left to right and like from left to right and from right to left. So we need the following lemma, that if q is at least 3 prime and s is not significantly smaller than t, we want s to be at least some log of t. Now, if you take a random s by t plus minus matrix, and you fix any two vectors, one in zq to the s and one in zq to the t, with the only restriction that you want the sum of the coordinates to be exactly the same mod q, then the probability that the sum of rows of the matrix sums to V and the sum of columns of the matrix M sums to U is 1 over Q to the T plus S minus 1. Okay? Any questions? So this Q to the T plus S minus 1 also says that it's a uniform distribution, right? Because the number of pairs UV that sum to exactly the same residue mod Q is exactly Q to the T plus S minus 1. Okay, so that's what I wrote here. And clearly, if the sums of UI and the coordinates of UI and VJ are not the same, so clearly there is no such solution, right? Because 1 transpose M, M times 1, you just sum up all the entries of the matrix M, so it must be the same residue class. And again, there are exactly Q to the S plus T minus 1 such pairs, and therefore it just means that the pair 1 transpose M and M times 1 is just approximately uniform distributed among all the feasible solutions. And as I stated before, it just means that we can view it not as a matrix, as bipartite graphs, and you can just fix the degree sequences mod Q, and you know that the probability to see such a matrix is roughly 1 over Q to the S plus T minus 1. So you also get a very tight counting, get that the number of such graphs with this fixed degree sequence is 2 to the S times T times 1 plus T to the lower 1 divided by Q to the S plus T minus 1. Right, so it's a quite exact counting. And now I want to switch to a completely unrelated problem before I show you the proofs. So suppose that you take an Mn to be a randomly chosen n by n plus minus 1 matrix, and then we can define, I didn't write it here, it should be symmetric. So suppose that you take M to be an n by n symmetric plus minus 1 matrix. And then we can ask, what's the probability that Mn is singular? Okay, I missed the word symmetric here. And there is an old question of Weiss, like that he asked, is it true that Pn is just like little of 1? So it's conjectured that this probability is actually very close to 2 to the minus n. But just the question of whether like Pn is little of 1 was only settled in 2005 by Costello, Tau, and Wu, that they showed that P of n, like the singularity problem for symmetric matrices, is like big O of n to the minus 1 over 8. And since then there was a little bit of work, like Guyen showed that this probability is n to the little omega of 1. Roman Vershinin showed that it's 2 to the minus roughly n to the c for some unspecified small constant c. Together with Vishesh Jan, we showed like that we can replace this c with 1/4. And like quite recently, so Campos, Matos, Morris, and Morrison, they further improved the constant, and they show that P of n is 2 to the minus square root of n roughly. So the main obstacles in all of these approaches for the singularity problem of random symmetric matrices are just like that all the approaches, they use more or less the same structure, that we do row by row exposure to reduce the problem into a problem about the distance of a vector from a hyperplane. And then we want to use some decoupling trick due to Costello, Tau, and Fu in the first paper. And all these arguments are quite lossy. So actually in the last paper of Campos, Matos, Morris, and Morrison, they even like wrote a nice paragraph to show that using this approach, you cannot do better than 2 to the minus square root of n. So basically they prove the best bound with respect to this approach. So we are looking for new approaches. So here I give a more direct approach that avoids these obstacles, but probably create other obstacles, because unfortunately I cannot prove any super impressive bound. But what is nice here is that this turns this problem actually into an exercise in an advanced class. So the following lemma is quite similar in nature to lemma 1 above that I will sketch the proof soon, slightly more technical. So here I prove that if you take Q to be any prime between 3 and n to the 1/2, let's say ignore the logs for a second, it's not really important, and you give me a vector v, any vector v in zq to the n, with no entry that appear more than n minus n over log square n many times. Okay, so I just don't want the vector v to have, like, let's say more or less the vector v to be too large in terms like proportional to constant, okay? Then the probability that mn times v is 0 is roughly 1 over q to the n. Again, mn is a random symmetric plus minus 1 matrix. So this is the key lemma that I will sketch the proof soon. So let's imagine that we have such a lemma, that we know that every vertex with no entry that appear more than n minus n over log square n many times satisfy the following thing, that the probability that mn times v is 0 is more or less uniform, like 1 over q to the n. And we will need another simple observation that for every vector v, which is not the 0 vector, let's say that you give me a vector that has large level set, so any non-zero vector, if you think about it for 2 seconds, you can convince yourself that we always have this trivial bound, that the probability that mn times v is 0 is at most 2 to the minus n, right? Because we can just look at one non-zero entry of v and just condition on the rest of the matrix except of this specific column. And then using these 2 observations, I can prove you the following theorem, that P of n is big O of log square n over n to the 1/2. So let me first sketch the proof to show you how to deduce the theorem from the lemmas. And then for the remaining time, I will talk about the proof of the lemma. So the first thing is, let's work over ZQ with Q, which is the largest that I can take in this lemma. Okay, so this is the main obstacle, that I cannot do it. Okay, I can do it for larger Qs, but not much larger. So I just wanted to keep it simple. So here, the largest Q that I can afford myself to take is around n to the 1/2 over log square. So let's fix Q to be theta of n to the 1/2 over log square, and observe that the probability that mn is singular is upper bounded by the probability that mn is singular over zq. So let's call it p prime n. Okay, so this is a trivial observation. And now let's define a random variable k to be the size of the kernel of the matrix mn, of the random symmetric matrix mn over zq. And so basically we want to discretize, to completely discretize the problem and to work into in a finite set. So we want to work in zq to the n, and observe that the expected size of the kernel is just the sum, right? By linearity of expectation, is just the sum over all vectors in zq to the n of the probability that m times a equals 0. And so what's the goal? The goal is just to show that this expectation is at most some constant. And then by Markov's inequality, we obtain that p prime n, the probability to be singular over zq, is at most constant over q, right? Because what does it mean to be singular? It means that you have a kernel of size at least q, right? Because the kernel is a vector subspace of zq to the n. So by Markov inequality, we get that p prime n is at most this constant that we see here divided by q. Any questions? So to this end, what can we do? Just let's define some fancy L to be the set of all vectors satisfying the assumptions of the lemma. The assumption of the lemma, let me just remind you, what does it mean? These are the assumptions of the lemma, that all the vectors with no entry that appearing more than n minus n over log square n many times. So this is the set fancy L. And now we can split the above sum of the expectation as follows. We can take the sum over all vectors in L and the sum over all vectors not in L. And then by the lemma, so what do we know? We know that if A is in L, then the probability to be 0 is roughly 1 over q to the n. And there are at most q to the n such vectors. we have this one here at the beginning. This is just from the all zero vector, right? If A is the all zero vector, so the probability that M0 is 0 is 1. And vectors not in L, we are going to use the trivial bound, 2 to the minus n. But let's count how many such vectors exist. So you need to choose n, or at most n over log square n many coordinates, right? That they're complement, right? So basically I want to choose n minus n over log square n many coordinates that will be constant. So this is times q because you decide which constant to put there. And in the rest, just do whatever you want. It's q to the n over log square. And the nice observation here is that if q is polynomial, so q to the n over log square n is sub-exponential, and also n choose n over log square n is sub-exponential. So 2 to the minus n just kills it. Okay, so we get that the expectation of k is at most 2 plus little of 1, and this completes the proof. So let me remind you the lemmas again. So lemma 1, we want to show that if you take a random m by m symmetric plus minus 1 matrix, and v is in zq to the m, then the probability that m times 1 equals v is roughly uniform. So I will prove this lemma because it's a bit simpler than the lemma for the singularity problem. But for the singularity problem, if you are curious, I've just uploaded to archive. It will appear tomorrow, hopefully, and you can just see it. It's like a 3 pages long paper. And the second lemma is a bit harder, so I'm not going to prove it now. So this is a little bit more complicated than lemma 1. So let's prove lemma 1. So fix some v in zq to the m, and let's define eqx. This is just going to be e to the, oh, I forgot an I. So this is just e to the 2 pi I x over q, just the q root of unity. And then we can write the following, that the probability that MA equals V, if you fix some A, but soon I will switch this A, I will just think about it about the all one vector. So the probability that M times A equals V is the expectation of the delta function, right? Of the indicator function of MA minus V equals 0, okay? This is just the expectation. And now we can expand it and observe that this Kronecker delta function, we can write it as 1 over q to the m, and summing up over all the vectors in zq to the m, and this is the expectation of EQ of L transpose times MNA minus V. So if you are not familiar with this argument, you just need to think about it for 2 seconds, because this is like a trivial, this is really a trivial identity that, well, actually I can write it. Okay, so I don't have access to other files while on large. So this is a trivial identity. And now I want to calculate the expectation. So this is like writing 1 over q to the m, sum over all vectors in zq to the m. So you see that we have this part here, EQ of L transpose minus V, that there are no random variables here because all the random variables appear inside Mn. So we can isolate it. So we have EQ minus L transpose V. And then here we have the expectation of EQ to the sum. So now I calculate the sum, like L transpose MNA. So when we expand it, so we just see a sum over all the entries of the matrix times the entry times Li, the ith coordinate of L, times Aj, the jth coordinate of A. And if we want to write it a little bit more, so this sum, I want to write it in a nicer form such that it will be a sum of independent random variables. Observe that it's a symmetric matrix, so Mij equals Mji, right? So I want to collect them together. So we can just write it as the expectation, and the sum, I can write it as a product because everything is independent now. I can write it as the expectation of EQ of Mij, and what is the coefficient of Mij is just Liaj plus Ljai. And now the nice observation, that's why it was easier to work with plus minus 1 than 0, 1, is that if you take an expectation of EQ to the Mij times something, where Mij is plus minus 1 with probability 1/2, so we just get a cosine. Right, so this is a routine calculation to show that the probability that MA equals V is just 1 over q to the m plus 1 over q to the m times the sum we're running over all L's which are not 0, and product of these ugly cosines. So now for simplicity, let's assume that A is the all one vector. So basically I'm going to prove lemma 1, and we obtain that the probability that m times 1 equals v minus 1 over q to the m, right? This is our guess. We want to show that it's very close to 1 over q to the m, is at most this ugly expression that just comes from this calculation, right? So we have the probability that m a equals v minus 1 over q to the m is this thing. So let's call it an error. And then we can use triangle inequality and get the following expression. And now A is the all one vector, so we don't have LAAJ plus LJAI, we just have LI plus LJ. And therefore, it's just enough to show that ignore this 1 over q to the m, just the sum of products of cosines is little of 1. If we can show it, so we are done. And in order to estimate it, we need the following very simple statement. So I will tell you the propositions and then immediately their proofs to show that it's really simple. So suppose that L is some vector with support of size at most m over 2. Then for at least s times m minus s pairs of indices, we have that Li plus Lj is not 0 mod q, right? And this is clear because just imagine that I give you a vector with support of size s, right? So let's take the support, right? And the complement of the support. And clearly, if you take an entry from the support plus an entry from not from the support, so you get a sum which is not 0 mod q. And proposition 2, suppose that you have some vector L with support which is large, right? So just said at least q, but it's not really important. So here if the support is at most m over 2, we have some bound. And here basically I want to say if the support is at least m over 2, but it works even for smaller ones. Then for at least s square over 2q square pairs of indices, we have that Li plus Lj is not 0 mod q. And how do you see it? It's just like if we have a large support, suppose you have a support of size s, so you have a level set of size at least s over q, right? You have at least s over q entries, which are exactly the same residue, mod q, and is not 0. And because q is a prime, so for non-prime, we need to work a little bit, not really harder, just to take 2 level sets. So because q is prime, so we know that 2 times non-zero is non-zero, and therefore all the pairs in some level set, which is s over q choose 2, many pairs, we have for all these pairs that Li plus Lj is not 0 mod q. So these are the 2 propositions that we need. And we will also need a very simple estimate that cosine of pi m over q is always at most e to the minus 2 over q square, as long as m is not 0 mod q. Okay, if m is 0 mod q, so it's just 1. Otherwise, we have a little separation from 1. And now we can prove we can complete the proof, because let's take this error. So let's go back to error to see it. So this is our error. So we can write the cosine, we can upper bound them by e to the minus 2 over q square in case that Li plus Lj is non-zero. So I want to know how many non-zero combination Li plus Lj I have among all these m choose 2 many terms. So I can just write it as a sum of e to the minus 2 over q square times a of L. What is a of L? Is just the number of pairs ij for which Li plus Lj is not 0 mod q. Okay, so that's what I need. And now we can split the sum according to the size of the support of L. So if the support is of size at most m over 2, so we know that AL is of order, where is it? S times m minus s. And the number of such vectors with support of size s is exactly m choose s is at most m choose s times q to the s. And this is our gain, e to the minus 2 s times, I had to write here m minus s. No, because I already upper bounded it with m over 2. And you have this 2 over q squared just from the trivial bound of cosine. Plus for the other L's, if L has a large support, so there are at most q to the m such vectors. And for each of them anyway, we get a much better bound from the proposition 2. And if you do the math here, you see that this is just little of 1. So this completes the proof of lemma 1. Lemma 2 I cannot sketch because it's a little bit longer. And so let me conclude with some open problems. So first of all, I think it's quite interesting to show, can you prove theorem 2 or also the theorem of Scott for the odd case with T equals Q, right? So with T equals Q, we don't know what to do because then the expectation is basically constant. And so it's not clear if you can partition to only Q sets with some fixed degree sequences. And I think something that sounds interesting to me, I didn't try it, is can you prove similar results for hypergraphs, right? I just like, I don't see like a simple way to extend these arguments to hypergraphs. And more interesting problems is about this singularity problem that I talked about. Can you improve the singularity probability of random symmetric matrices to something exponential using this approach or using any other approach? This would be very interesting. Okay, thank you.
Okay, thank you, Asaf, for a very nice talk. Before unmuting everyone for the virtual round of applause, are there any questions? Recorded questions? You've kind of taken away my question. I wanted to ask what happens in the, I mean, is it known, is there some result known about the hypergraphs, or because that came to me? Yeah.
No, but it sounds interesting. I haven't tried yet, but it sounds complicated enough.